Hello and welcome to this Inspiring Science Education Hangout. My name is Dr. Pamela Gay and I'll be your host. In this series of live events and training videos, we will be presenting timeless astronomy education materials that are designed to help students learn through a variety of inquiry activities that we will be providing for you, and also hoping that you will take the time to, well, customize for the needs of your students and then share back with our community. Today we're going to be talking about the four forces that hold our universe together and that also, well, they have the potential to tear things apart. These forces are controlled by special force communicating particles called bosons. And in a weird twist of fate, these special bosons control how every other particle, so this is particles controlling particles, how every other particle that makes up everything from planets to people interacts with everything else. As to give you a quick overview of how this Hangout is going to be structured, since this is such a complex topic, I'm going to start by giving you a very brief overview of what the forces are, what they do and how they mediate interactions throughout our universe. And then joining me, I have a pair of people actively engaged in working on exploring particle physics. I have Andre Tanico Mendez, whose name I'm afraid I probably pronounced horribly, and Dennis Damasio, both joining me. These are scientists that are working with data from the CERN accelerator that is out in Switzerland, and they have been actively working on studying bosons and other particles, and we'll be talking about that. Once we're done with that interview, I will be overviewing a new scenario that we're in the process of putting together for the Inspiring Science Education learning community to help you bring all of these things that you're learning today into your classroom. So if you have questions, this is a complex topic, and I welcome you to ask those questions. If you're watching this live, either on Google Plus or over on YouTube, you should see that the window that I'm talking in has a little live Q&A button, probably bright yellow and somewhat obnoxious. You can use that to ask questions. Now, if you get to talking to one another using that, I'm not going to be able to find your questions. So please hold the chatter for either the comment feed on Google Plus or over on YouTube, and just use the Q&A app for asking questions. I can already see that we have a fairly large audience with Nazi Graziano, Peter Waldman, Pavlos Theodro, so many others coming in from all over the world saying hi and, well, welcome. So we're all kind of used to interacting with forces in a variety of ways. If I take the remote control for my camera and drop it, it falls. This is the mass that makes up my remote control, well, getting interacted with the gravity of the Earth. So both this object is pulling on the Earth and the Earth is pulling back, and it just happens to be the Earth is so big that just like a toddler trying to pull over a sumo wrestler, the toddler ends up pulling themselves into the sumo wrestler just as the remote ends up actually pulling toward the Earth as the Earth pulls back, but we only see the remote moving. That's perhaps the most common way that we deal with forces in a way that we constantly think about. Falling over is something most of us try to avoid. But then we also start to see force when we deal with magnets. So I have chains of beads that are quite happily going to attract one another if I orient them one way. But if I instead flip them around and bring them together, they're going to repel apart. This is the magnetic force. Again, something we're completely used to. But what we're not thinking about is the reason that these beads attract to one another rather than flying through each other to make one giant bead is because, well, first there's protons and electrons making up the atoms in these beads. But then those protons and atoms, well, they're also prevented from coming together to merge into single protons by other forces. So the electromagnetic force is pulling the electrons and protons together, while at the same time we have other forces at play holding the cores of those atoms together. Now, to help you understand this, I'm going to do the standard scientist thing of subjecting you to a diagram. So let me screen share some images with you. And again, feel free to ask questions at any time. And if you like the questions that you see, check them. That will help me understand what you're most interested in having shared. So this diagram that I'm showing you is one that takes all of the different particles that make up everything and breaks them down. I'm giving this to you as a quick overview to show you where we're going. You can see listed in blue down the right, photons. This is the particle that we often perceive of as just light. Then there's this particle you may not have heard of called a gluon, and then a Z boson and a W boson that have different characteristics. Each of these different particles is responsible with different forces, and what's missing from this diagram, because it doesn't fit in neatly, is gravity. Gravity doesn't fit in neatly pretty much anywhere. It has its own boson called the graviton, and also not fitting in neatly with this little diagram is the Higgs boson, which is what gives things mass. Now, I'm presenting this to you so that you can see that we have a variety of different particles. Up at the top, we have these 6 purple boxes that contain the names and symbols and information for the quarks that make up particles that you're familiar with, the proton and the neutron, and a lot of particles you're probably not as familiar with. We also have the basic particles that are called leptons. These are things like electrons, which we're used to thinking about as electricity. And these leptons are also basic particles that can't be broken apart. Now, this basic diagram is what we often refer to as part of the standard model of particle physics, that model that says these are the fundamental things that will pretty much make up everything else that we deal with in our universe. And getting at this 3-color, lots of information diagram is something that has been a long time coming. It kind of started with Newton, who is said to have been hit in the head by an apple, but not said by historians to be hit in the head by an apple, but it makes for a great diagram anyways. We're all used to perceiving things falling, but for millennia, people knew things fell. They knew they fell periodically. Every child learns that while learning to walk, but they didn't know why. And it was Newton who started to postulate the idea of how we can mathematically describe all of this through the force of gravity and through the ideas of acceleration. And this got us the first force, which interestingly is also the first force to have stood by itself in the formation of our universe during the Big Bang. From there, we went on to realize that, well, there's chunks of rock that have weird attractive properties. These are the natural magnets that are out there. And we've since learned for industrial purposes how to manufacture magnets. And magnets have this amazing ability to attract things on one side, repel when you turn them around, and if you coat them with little bits of metal, you can start to see what we call field lines, lines of how force is distributed around these magnets. Over time, and with a lot of experimentation, folks started to realize in the 1800s that this is also how electrons and protons are attracted to one another. And we started to get this idea that there's this combined electromagnetic force that interacts with everything that has charge. But unfortunately, things they got more complex as we delved further and further into the atom. We started to wonder, what is it that holds together at the center of atoms? If you think about it, if we didn't have a force holding one proton to another, our entire universe would be made up of very boring protons, otherwise known as hydrogen, kind of floating around going, "Hi, I'm a proton," and electromagnetically attracting themselves to electrons, without some force to allow multiple protons and neutrons to bind together. We wouldn't be able to have helium. We wouldn't be able to have carbon, which is what allows life to exist. We wouldn't be able to have the oxygen you breathe. And through lots of experiments, people started to realize there's this nuclear force. We sometimes call this the strong force, sometimes call it the strong nuclear force, sometimes call it the nuclear force. How you see it referenced will depend on the age of your textbooks or the age of the person writing the magazine article that you're reading. This strong nuclear force is what allows neutrons and protons to hold one another together, and it also overcomes the fact that, well, electromagnetism actually wants to fling those protons apart. When we discussed the learning scenario at the end of this lesson, I actually have a really neat exercise to show you on how you can get your students to understand how one force is trying to push the protons apart, the electromagnetic force, while another force, the strong nuclear force, is actually able to bind those protons and neutrons together. Now, as we continue to delve further and further into the atom and further into protons and neutrons and the other subatomic particles that make up unstable matter, we realized, wow, protons are not fundamental particles. There are actually things inside of protons. There are things inside of neutrons. Inside is not the best word, but that's unfortunately how all of the images you're going to find show it. Protons and neutrons are made up of combinations of 3 quarks. And these quarks can actually change identity because of interactions with what's called the weak force. You can go from having a neutron, which is a combination of 1 up and 2 down quarks, to having a proton, which is 2 up quarks and 1 down, through one of these weak force interactions. Now, to conserve charge and other complex parts of particle physics, you do end up having an electron and an electron antineutrino that get flung out in this process. But it's things like this form of change, going from an up to a down or a down to an up, that allow radioactive decay to exist. And in astronomy, it's actually extremely important because in things like white dwarf stars, the matter is so compact that protons weren't able to push one another apart, and electrons weren't able to push one another apart. And all of these particles got mashed together to form neutrons while giving off anti-electrons, otherwise called positrons, and neutrinos as the core of a star collapsed from a white dwarf down into a neutron star. So you have white dwarfs that are extremely compact. You add too much matter to those, you get a supernova, and sometimes you get a neutron star. So all of these different things are mediated by different forces. Again, this is a lot of information. This is all going to get written up in the scenario we're going to give you. Now, to try and put all of these pieces together, we have these 4 forces. The strong force, which is what is holding atomic nuclei together strongly, is a good way to remember it. And we needed to figure out, well, what's holding them together? And it turns out that there's a particle called the gluon that is communicating this force. We have the electromagnetic force. This is what binds the electrons to the protons in atoms. This is what causes light to be emitted when electrons jump energy levels in excited or no longer excited atoms. This is what causes your magnet to stick to your refrigerator. All of these things that we observe come from the electromagnetic force. Gravity, with its theorized graviton boson, is what holds the moon to the Earth, holds you to the Earth, holds the Earth to the sun, and quite literally holds all of the things in our universe that are interacting with one another together. And then we have that weak force, that force that allows one type of quark to change to another type of quark during various types of radioactive decay. It's also part of what allows stellar cores to collapse into neutron stars, and it plays a role in the nuclear reactions that take part in all stars, including our sun. Now, getting back to our model of the Standard Model, we're now in a position where I can say we have four forces, and we have four different communications bosons that I show here, as well as the graviton. So we have the photon that is tied to the electromagnetic force. We have the gluon that glues the centers of atoms together, the nuclei of atoms together. It actually takes two different bosons to mediate the weak force. Gravity, as I said, does not play well with others. We have the graviton that goes with it and does not show up in this diagram. Then we have the quarks. Up and down are the ones that make up all the stable particles that you're used to dealing with, protons and neutrons. And then we have the leptons. These are things on the stable side, like electrons that are in atoms, and the electron neutrino that I showed you as part of what happens when you have that proton turning into a neutron, or vice versa. All of these things, again, also fit in with the Higgs boson, which is what gives things mass. Now, that was a very quick overview that will hopefully help us get into an awesome discussion with our scientists who are here visiting with us today. I need to take a moment to unmute their audio. And for those of you just turning in, welcome. This is the Inspiring Science Education Hangout. This is a project that is tied to the Inspiring Science Education website, which you can use to find educational materials to better teach science to your children. And if you're not a teacher, point this resource out to a teacher you know so that they can improve science education wherever they are in the world. So with me, I have Andre David. And I also, he figured out how to use the lower third. That's excellent. And I also have with me Dennis Damasio. And welcome, Dennis. I'm going to start with you. You're a research scientist from Brookhaven National Lab who's currently over in Europe working with the Atlas Project. Welcome. Would you like to tell our audience a little bit more about yourself?
Well, hello. Good evening for those that are in Europe. Well, good whatever morning if you're in LA, and so on. So this is a too big word. So yeah, I've been here in this project. So I'm here at CERN. So I'm working associated to one of these very large experiments that we have. In this big collider, so the Large Hadron Collider that we have here in Geneva. I work for what's called the Atlas experiment. So it's let's say, the biggest one. So Atlas reminds people of big things. So it's the biggest one of the experiments. It's not the heaviest one, which is, we are going to hear from Andre about the heaviest one. And we are very interested in understanding basically so the components of nature and the components of matter and the components of force. So what are the forces? So of course we have to try to understand how the different bosons, so if that's the topic of the day, interact with each other and also with matter. So this is something that is very relevant in the work that we do here. So for instance, we're going to discuss that a bit more in details later on. But we want to, for example, we were searching for this Higgs boson, which Pamela just mentioned. And this particle is, well, we usually cannot see it directly. So I'm much more an experimentalist, so I'm going to talk about things that happen in the experiment, of course. But a particle like, for example, the Higgs boson, we can never see it directly. What we can see is usually that it gives other types of particles. It disappears very quickly, so that's a characteristic of the Higgs boson. And it gives, for example, photons. And photons are, well, then you have some special detectors to find the photons. I don't know if I'm saying too many things. I hope not. But the whole thing, well, why I'm discussing all this is that photons are the type of particles that we're very interested in detecting. And I work, for instance, in trying to make good algorithms to be able to find the photons that appear in our detector. So that's a global picture, including bosons, what I do, and so on.
That's excellent. I'm really glad that you're able to join us. Andre, you are also a scientist working with CERN, but you're actually physically located somewhere else. Could you tell us a little bit about where you're at?
Oh, I'm at CERN.
Oh, you're just in a different part of CERN. Okay, so sorry.
Yeah, we're just in different. I mean, CERN is quite big. I mean, the Large Hadron Collider has a 27-kilometer perimeter, so it's easy to be in very different places at the same time. So, as Dennis was saying, I work in the other experiment, the one which is the heaviest. Actually, it's denser. It's smaller than Atlas. That's what the C stands for. It's for compact. And I've also been working looking for the Higgs boson, and it's true that bosons are very interesting particles, because if you think of particle physics as a theater play, the actors are fermions, but the actions are bosons. So the script is all about the bosons.
So that actually really gets me to the first question that I had for you. What ignited the search for bosons, or made people start thinking, hey, bosons are a thing? It's not like when I take my little magnets and allow them to attract to one another, I see flashes of light. What caused scientists to start to think, hey, there's a particle that's communicating this force?
Well, you want to go ahead?
Andre?
Oh, me. Sorry. So the thing all stems from the theoretical description that we have for these interactions. So the observations are crucial in establishing what makes sense and what does not make sense. But then when you write down the equations, and some of them are pretty daunting, you see that there are these fields which would reflect themselves as bosons, so that they end up predicting particles which have integer spin. Now we call them bosons.
So integer spin. What does that mean?
So that's I mean, boson. The origin of the word is from Bose, who was an Indian physicist who worked with Einstein in something called the Bose-Einstein statistics, and that's one particular way we found that quantum particles, if you want, or particles at the quantum mechanical level, behave. So you have this very fundamental distinction between bosons and fermions, because, for instance, as you cool them down, fermions will stay each one in its own place, whereas bosons will start clumping up together in the same point of space, which is really amazing and gives rise to all sorts of weird phenomena.
Can you see the image of Bose, the guy that gave the name to Bose? Okay.
Yes, thank you for sharing that. So it sounds like particles have a variety of different characteristics. We know that charge is a thing because we've all experienced in various ways. So We see protons and electrons with their positive and negative charge. You've now mentioned some of them have spin. I know as a result of quarks, we have to worry about things called color. And all of these different properties come in to, well, basically it's puzzle pieces that build the standard model of these things fit together this way, therefore we must have this piece. It's like when you're building a puzzle and you have the whole, and now you have to find the thing that fits in that shaped hole.
Yeah, and there's also this point which I find particular, well, especially if we are talking to teachers who are interested in explaining some of these things to students. One very used way of picturing what bosons are. So they are the, let's say, the particles that communicate in some sense the force that they are transmitting, right? So of course we could talk about more complicated things, but in a very simple example, for example, imagine that we have two students, each one in a boat, okay, and this is a very used example. Or, okay, maybe in a supermarket, a little cart, right? if you want to not bring water into the picture, but then you give to one of them a very, like a basketball, and then they throw to one another, so they keep throwing. And what's going to happen with time is that they are actually communicating through the ball momentum, and they are going to start to drift apart. So that's a bit a way of thinking. So you have two massive particles which are exchanging this little particle, which is the basketball, right, the boson in the middle, and then they are suffering some action. So they are getting apart because of that. So it's a way of communicating momentum, if you want, in some sense.
So when I take my favorite little magnets and they start to repel each other or they start to attract each other, I don't actually see flashes of light as the photons fly around communicating that force. And I know this is extremely struggling, especially to children who are like, but I don't see it. How do you explain the fact that there are bosons responsible for this force interaction, and, well, where's that light coming from and why don't we see it?
Well, calling it light, you see, the issue, I think, stems from the fact that visible light is what we are used to call light. But there's also X-ray light, there's radio wave light. The transmission of the electromagnetic force comes in all sorts of forms and manners, and they do not need to imprint our eye with something that our brain then gets excited about directly.
Yeah, like for example, heat wave is another form of light, if you want. So, and you don't see it, right? So you feel it, but you don't see.
So does that mean if you had lab equipment, you could detect those photons that are doing the communications, or is it more complicated than that?
I think is just like that.
Okay. So sometimes you will see, just to warn you, as you read about this, you'll see various authors and scientists talking about how it's virtual photons that are doing the communications. Just to break it down, as this is not quite what we're used to, where light is coming out from electrons transitioning between different energy levels. It is something where it does get discussed somewhat differently. What?
Yeah, I didn't want to go into that point.
No, it's all right. I like to give them a good warning that this is the same particle, but it's discussed in different ways and doesn't exactly come about in quite the same way. So we've been looking for these bosons pretty much ever since people started putting together this puzzle of the standard model of, okay, we have these bits, therefore we must have this bit to fit everything together. Photons were fairly easy to detect because we wouldn't see the world if we couldn't detect photons. But getting at the other bosons that mediate force has been a bit more complicated. Can you help our audience understand how it is that we've been searching for bosons?
And so here, well, sometime, now I don't remember exactly the year, but sometime in the end of the 60s and the beginning of the 70s, there was, maybe I should not, okay, maybe I'm going a bit ahead in the picture, but there was this, well, the initial proposal for this standard model, which would be a complete description of the whole set of particles that do the whole business of transmitting the force. But maybe I'm saying I'm actually going a bit ahead because you want to discuss how the other type of particles
Yeah.
were found.
Yeah.
Okay, maybe Andre can complement. Sorry.
Well, so I was thinking of a sort of chronological approach.
Yeah,
So
go for it.
the standard model can be very fundamentally sort of split into quarks and gluons, and photons, leptons, WZ, and the electroweak and the quantum chromodynamics,
Yes.
for a lack of big words. So I think that the first boson that we were really looking for was the gluon. And this was actually found by colliding electrons and positrons, and these annihilate into a photon, which then decays into a quark and an antiquark, and sometimes a gluon. So these events would produce a quark, an antiquark, and a gluon. So they would produce 3 jets of particles, and these 3 jet events were evidence that the gluon had some sort of correspondence with reality, because the gluon is a theoretical concept, right? So this was in the late 70s, and then in the early 80s, there were a different set of experiments who were trying to understand where were these elusive W and Z bosons, and they found something like 2, if I remember correctly, and that was like a discovery with just a handful of such events.
So, Andre, do you want to explain the diagram you just brought up, which is very similar to the one that I was showing as well?
Yeah,
well, actually, I did it.
I can share it. So let's see, where can I share this?
If you mouse over the window that we're talking in, no, turn that one off. If you mouse over the window that we're in, there is a button on the far left that is green with an arrow in it. That is a screen share button that will allow you to screen share.
Green, there, that one.
Yes.
And now the problem is there are too many windows. Okay, very good. So this one. So this is the diagram I was referring to. It's from the Wikipedia gluon page.
Discussion. Yes.
And you see here on the right side, there's the collision between these 2 electron and positron, and then they annihilate to produce a photon, and then when you decay, you end up having a quark, an antiquark, and a gluon. So if you could not have 3 quarks, because you would violate charge conservation, because quarks are charged, but the gluon is neutral. So the only way these things could happen were via having a gluon. So that this extra, I mean, the way these things look. Okay, this is another example. So this one is the one through a special case, which has this. You see this on the right.
Yes.
There is this special sort of racetrack with a B and a B with a bar, and that was another case on how you could see that there were all these 3 jets coming out.
So for those of you who aren't familiar with these diagrams that are basically lines and squiggles, these are what are called Fermi diagrams. They are part of the language of particle physics, and Feynman diagrams, rather, and they were created by Richard Feynman as a shorthand for all of the interactions that we end up talking about with different combinations of squiggles, for lack of a better term, relating to different kinds of interactions and different kinds of particles. So I'd love to see both of your charming faces back, if you could stop screen sharing for a moment. So when we look at the standard model diagrams that have been brought up, gravity doesn't crop up with it, and we don't talk about discovering the graviton, largely because it's massless and thus not really detectable. How is it that we have this boson that doesn't fit in the standard model, and where on earth did the idea for the Higgs boson come into play as well?
So if I can start with the last part of your question, I think it's better for me to start there, and I'm going to unfortunately share some
Okay.
but it's quite quick. So yeah, because in this diagram that I was sharing before, let me come back to it. This is the one. Yeah. So you see that there is over there the photon. It shows up quite well, and you see that there is a number. So the first number that is in the square where the photon is a 0. Okay, which means that the mass of this particle is 0. Okay, we're going to go step by step. So if I go back to that example that I had before, it's kind of you're really looking at instead of using a very heavy basketball, you're really throwing a very, very light ball, whatever it is, okay, to the other one. So you can try to eventually make the other person move because you're really sending it very fast with a lot of momentum, but it doesn't contribute too much to the movement. The fact that this particle, this ball, doesn't have any mass. But then now you go to the case, to another case where you actually have a very, very massive ball, like a bowling ball, for example, and then you try to throw this one. So there are two things that are going to happen. First, that you're going to be able to communicate, maybe eventually. It's going to be easier to communicate the movement. The other thing is that it's much more likely that you're actually will only be able to transmit the force not to very far distance, because that particle, you're not going to be able to throw it across a huge field, for example. So the fact that these particles like W and Z, you see that there's a big number over there, 91.2 to the Z and 8.4 to the W, and the fact that we cannot observe them at very long distance, like the photon. The photon, for example, can observe at very long distance, right? We get the photons from the sun, for example, which are very far away. But the W's and Z's, they operate at really small distance, like the nucleus of an atom. So at the end, what I think I want to say is that these particles, in order to be very short-ranged in the transmission of force, they have this characteristic of having mass. So to describe why these particles have different, or why, how the mechanism that they acquire such mass, then in the I think late or early '64, so more than 50 years ago, there was this guy Peter Higgs and others, so that started to try to build together a framework so that they could explain the short range of such kind of particles, of the action of such kind of particles. And there you get the notion of maybe the question about whether they really have some property, or that's why they are short range, because they have very huge mass. And so at the end, the whole mathematical concept is a bit complicated, but the idea is that by iterating more or less with what's now is called the Higgs field, a particle would have more or less mass. Particles that do not iterate at all, like the photon or the gluon, they have zero mass, so they can go infinite distance if the distance as big as the universe, which is not the case for these two other ones. So kind of start backwards. I hope that helps. Maybe Andre can complement.
Yeah, Andre, do you have anything that you'd like to add?
Yeah, because you started by talking about the graviton, and the graviton is right now something hypothetical, because we don't even have a theory for that. I mean, it's really problematic that we have the standard model is quantum field theory. So it's something we can write down and do calculations and all of that, but there is no quantum theory for gravity. And if one day we will have a quantum theory for gravity, then the graviton will appear naturally as the conveyor of the gravitational force. And the problem with this is that gravity is fundamentally very different in geometric terms, if you want, and the interaction is extremely feeble. I mean, to give you an idea, the gravitational force with respect to the force that keeps the quarks inside the nucleus, which is the strong force, it's 10 to the minus 41 times weaker. So that's 0.040 zeros and the 1 times weaker. And that's also part of the problem.
And just to bring that back to the fore, that amounts to, I have these couple millimeter across balls that are being attracted by the giant planet Earth that's below my feet, and the magnetism is able to overcome in these little tiny balls the force of gravity from the giant planet Earth, and we aren't capable of measuring the gravitational pull of balls this small without extraordinarily sophisticated equipment in environments that don't actually exist yet. So it's something where we can actually tangibly feel that difference in the pull of gravity versus the pull of the electromagnetic force, which has nothing on the pull that allows protons and neutrons to hold one another together in the centers of atoms. So we have this problem that gravity doesn't fit into the standard model. This Higgs boson is this weird appendix. Are there any other bosons that have cropped up inside, outside of the standard model that we have to account for when we look at the forces around us?
Inside, no. Outside, who knows? For instance, in supersymmetric theories, every single fermion in the standard model has a supersymmetric bosonic partner. So there could be out there, because that's something which is also unclear, is why is there this big fundamental rift between bosons and fermions? And in supersymmetric theories, you basically solve it by saying, well, there's nothing special about being a fermion because there is your supersymmetric bosonic partner. So there could be a host of bosons out there, but in what concerns the standard model, we're done.
And what Andre is hinting at is the standard model is basically people looking at a puzzle and defining what pieces must exist. This is largely like how Kepler looked out at our solar system and determined the mathematics that describe the motion of planets, the motion of moons around Jupiter. He came up with a mathematical framework, but he didn't have a fully hashed out understanding of why this math existed. With the standard model of particle physics, we're a little bit better off than that, but we don't have this fully fleshed out understanding of why this math works. And scientists like Steven Weinberg, who worked on the theory of supersymmetry, have been struggling to put together the Newton's theoretical framework of particle physics, if you want to carry the analogy further. They've been working to try and flesh all of this out and coming up with a variety of different theories where supersymmetry is one of the ones that has the coolest words in it. But we aren't yet in a position where we've been able to test any of these additional theories. For instance, string theory I've often heard described as beautiful, unprovable maths. So if any of these theories, like supersymmetry, are proven true, are there aspects of the standard model that we're going to have to throw out, or is it like Kepler's Kepler's equations for planetary motion, where what we have will still be true and we simply add on, or do we just not know?
Well, there is for sure a part of the business that we don't know, but I think your second option was the best one. So the standard model is quite well established, I think, and especially now that we have actually found the Higgs boson. So this is quite what this model was done to describe. It seems to describe it very well. There are, however, a few things inside the model and outside the model that are not yet completely, let's say, we don't have an explanation, or we are not completely, are not good explanations yet. So, for example, things that we still struggling with, and I'm not sure whether the theorists have any good explanation so far, is, for example, as you see in the diagram that we presented a few times, there are these three families of particles. And so if I want to say about some things that we don't understand inside the model, and we don't understand why we have the three families. So why they have so, let's say, similar characteristics between one family and the other, and just the mass is different. So this is something that is not completely understood. And if we want to talk about things which go outside the model, then we have things like dark matter that in principle is this weird method that we cannot see, that anyway looks like it's in our galaxy. For example, maybe in the center of our galaxy we have a huge accumulation of dark matter that explains why the planets can turn around the center of the galaxy and not drift away. So there is enough gravity to pull everybody together. So if these particles exist, we need to figure out what they are. And they don't look, or there's nothing in the standard model that seems to be a good description for that. So if this is the case, then we maybe are going to find another particle, hopefully in a few months from now. but this is, of course, the hope of an experimentalist. But so there are many things that go outside this model and that we still have to understand.
Andre, is there anything that you'd like to add?
So it's interesting that most people think of the scientific process as evolution and revolution, but in physics in particular, even if you have revolutions, whatever is the new paradigm must still simplify to what was the previous paradigm, because nature will still be nature and the observations that were done must still be respected. I mean, for me, the paradigmatic case is Newton's gravitation, which, you know, mg over r squared done. This is still valid for small distances and small masses with which, for instance, we live every day. But then if you want to go to galaxies and black holes and all of that, then it doesn't work anymore. And then you really need to get into Einstein's relativity. Now, Einstein's relativity was a revolution, but in the limit of small distances, it reduces back, if you want, to Newton's gravity. So even if you have a revolution, it will still contain the previous step.
Science is a process of steady progress forward with occasional leaps sideways or backwards. But in this case, we're pretty sure that it's going to be that steady progress forward, constantly evolving our ideas to increase our understanding, but not necessarily to throw out our understanding, which I know is a relief to people who can't buy new textbooks. So before I let you go, do you have any final comments that you'd like to share with our audience? I'll go to you, David, or Dennis, sorry.
Yeah, well, we got a lot of, let's say, publicity by thanks to this discovery of the Higgs boson. Now, recently, right? So in 2012 and 2013. So in 2012 we discovered the boson. 2013 we confirmed it was the correct boson, and so on. We do have actually. So this is it's very important to excite people about science, and to have things like this broadcast, because we really need to make people aware of the things that are happening in the realm of science. And for example, now we spend like 2 years just preparing our experiments. So I think Andre is going to say something similar. He also had an effort in CMS in order to be able to prepare for these new discoveries. So now actually this is quite interesting because as I said before, in the 64, so 48 years before the discovery of the Higgs boson, so you see that there was a proposal of maybe an existing particle that existed for 48 years, resisted to be found by 2 other particle accelerators, so it could not be found by 2 other particle accelerators. But people insisted and tried to find, and there were no evidences at all until sometime in 2010. So this was so it was important to keep doing this job of making sure that we are able to do such kind of research. And then, so why I'm saying that? I'm saying all that because, well, now we are actually in the LHC in particular, of course, that's what I'm more interested. We are now getting to the realm of many of the unknowns. So there'll be hopefully very interesting news to come in the months or years to come. And I think especially teachers, they might want to always get tuned to what we are doing here and elsewhere in terms of physics, science in general. Just an invitation, let's say, for people to not disconnect from science.
Sounds good. Andre, what would you like to add?
Okay, I would like to advocate fundamental research. It's not because we kept on making better candles that we got the light bulb. And it's not because we kept on making better light bulbs that we got LED lighting. So all of these things have required some fundamental research breakthrough in order to get better technology. So sometimes people fall in the trap of saying, but all of that is useless. Who cares about the Higgs boson? But the thing is that in previous experiments like those at LEP, people had to organize themselves because they were working in hundreds, and now we work in thousands. And that led to the Hypertext Transfer Protocol, which is this thing, the HTTP and the web. So there are many things that we do here which have no apparent applicability today, but which may actually have applicability in the future. I mean, I think there's this apocryphal story of, I don't remember exactly who was playing with electricity, and then the minister came and said, but what is that good for? And he said, well, you know, I don't know, but you will surely tax it when it's figured.
Understood. And so thank you so much for joining. And Dennis is showing us, showing us a beautiful picture. And I think this actually, what you're talking about with the huge collaborations and the many decades that it takes to accomplish basic research and these sorts of discoveries is something that we really need to create a teachable moment about. The various instruments at CERN weren't just built by the staff at CERN. They weren't just built by the 100 names at the top of the research paper. There were literally generations and generations of students involved, of random labor. I was an undergraduate at Michigan State University back in the 90s, and we were engaged in working on building components for Atlas back then. There are fibers in CERN that I'm responsible for the epoxy on, and that was decades ago in a lifetime far, far colder in Michigan. It takes hundreds to thousands of people to find the smallest particles. And I thank the two of you for being two of those thousands of people involved in finding the most fundamental parts of our universe. Thank you so much for joining us. You are welcome to disappear while I start talking about the learning scenarios that we're working on. And thank you so much for coming on today.
Okay,
right, thank you for having us.
Can I just say just one final thing? The picture I was showing before, it was a laser, and I was just wanting to show that because it's a laser is nothing more than a trail of bosons, so
Yes.
so I thought it would be interesting to end on that note. So,
excellent. So thank you so much, gentlemen.
Thank you.
Thanks, Pamela.
Thank you. Bye.
Bye-bye. So thank you for sticking with us. If you've ever watched edited TV or listened to audio on the radio, you often will hear folks like Jon Stewart say, and you can now go to the web to see the entirety of this, well, edited interview. You're watching this get recorded live. We don't have the benefit of being able to edit for time. So the show in the live recording will go over, and we will look into creating an edited version that is only 1 hour long. So if you're watching live, I'd encourage you to stick around while I go through the learning scenario that will tie in with the interview that we just watched. That was a tremendous interview that will continue to be made available in its entirety, along with the edited, check it out on the web version that will also appear on our Inspiring Science Education YouTube channel. For those of you joining late and not quite sure what you've wandered into, this is an Inspiring Science Education Hangout. This is part of the Inspiring Science Education portal to educational resources that we are working to design to build a community of teachers around the world who are increasing science education quality for students everywhere. As part of putting together all of these activities, let me start before I go into the activity into showing you where you'll be able to find these in the future. So I'm going to go ahead, and it's time for me to share my screen. So we have created a community on the Inspiring Science Education website that is designed just for this particular lesson plan. Within it, you can find a variety of resources. You can check out who are members, and hopefully that number 4 will increase by the several dozen of you who are out there watching this episode. All of this can be found by going to the inspiring-science-education.net webpage. It's a long URL that goes to a vast quality of information, so take the time to write it all out. When you get to this site, you can click on the community portal and check out all the different communities that exist within this site. The community that we've created for this lesson plan is where we're going to be uploading this lesson. And to show you an example from what we created to go with our last lesson, digging into comets, when the lessons go live, you'll actually have the ability to go in. Well, this is my lesson, so I can edit it, but you'll have the ability to go in and click this clone lesson button. It looks like the copy button in many different word editors. And when you click it, it allows you to take these existing lessons and edit them to suit the needs of your particular classroom. Now, when you edit these things by clicking the clone button, you are saying, I want to be part of a community that says, hey, I have this special need for my kids. Perhaps you have visually impaired students. Perhaps you don't speak English, you speak Portuguese. Whatever your reason for editing the lesson, either to translate it into a new language or to adapt it for the needs of your learners, we'd ask you to please upload it back into the system. Now, once it's in the system, we have the capacity, and I'm going to have to switch windows once this opens. We have the capacity to allow you to go in and look at the lesson, and there are both instructor versions and student versions. So everything that's uploaded into the system exists fully put together for both your needs and the needs of saying, hey, I need a handout to give to the students in my class. Now, the lesson that we're preparing to go along with this Hangout, which will include the edited version of that interview as part of the lesson so that you can share young real scientists talking about the work they're passionate about. Once that is posted online, it walks you through in a put together for your students kind of way, giving them a real understanding of what are the forces. So just as I started this particular Hangout by saying, we see gravity because things fall, We see magnetism because our magnets snap together. This lesson plan starts by having you do a very similar activity with your students. And once you've gone through that, hey, here's an introduction. You can get them saying, I wonder what are the different places that I experience force. And this gives you a chance to get your students thinking about the fact that the reason they don't fall through the chair they're sitting in, just like I don't fall through the chair I'm sitting in, is because the electromagnetic force is holding electrons to protons, because the strong force is holding those atomic nuclei in my chair that is not made of hydrogen. That strong force is holding those atomic nuclei together. So the lesson plan starts by having you drop things, attach magnets to things, and then go on to say, now let's think about, well, what holds atoms together? And this gives you a chance to introduce the strong force. Introducing the weak force is a bit harder because we don't generally experience the collapse of stellar cores into neutron stars. But this is a chance for you to pull up a beautiful picture of a supernova remnant that has a neutron star, perhaps a pulsar in the center. This, if you want, ties in beautifully with activities you may do in the future, like Pulse at Parks, which allows your students to get involved in listening to pulsars. Once you've introduced the concept of force to them, the next thing to do is literally break them into groups and say, hey, students, go forth. Brainstorm all the ways you interact with force, the fact that you're not falling through the chair, the fact that you're not falling off of the planet Earth because you don't have gravity holding you down, the fact that maybe you take a maglev train if you're in China, maybe you've run on the monorail at Disneyland. What are all the different places that we experience force? Once you've gotten them to talk about all the ways they experience force, the next idea is this thing of force at a distance and how different forces overcome each other. The opening idea to this is to return to, well, I have magnets that gravity is pulling them towards the center of the Earth. But as I bring them closer and closer together, they're eventually going to snap together as the electromagnetic force overcomes gravity. When we deal with atoms, we deal with the exact same thing. In this case, we have protons are trying very hard to repel one another, except when they get close enough, the strong force overcomes that desire for them to repel each other and allows them to stick together. And this is a tricky concept for students to learn, but there's an easy way using toys you may already have in your classroom to get this across. Now, I'm going to show you the ideal way to do this using a picture of things I don't actually have. And since I don't actually have this, I'm going to show you how I hacked it. So let me start by showing you the ideal equipment. What I'm about to show you, once my screen shares, is what's called a magnetic wand. These things look a little bit like a weird kitchen implement, but it's actually a magnet that's encased in plastic so that you don't have to worry about the magnet breaking. I don't know about you, but I have an entire drawer of broken magnets that have suffered very bad fates at the hands of college students and small children. Breaking magnets is not something that changes as your students grow up. These magnetic wands are a great way to save yourself money on magnets in the long term. And they come with a bunch of these little dime-sized pieces of plastic that have metal rings around them that you can then scoop up with that magnetic wand. Now, the little pieces of plastic we don't actually need for this particular experiment. What's important about this particular experiment is one side of the magnetic wand, when you bring it closer to another magnetic wand, is going to pull the two magnetic wands together. And the other two sides are sorry, if you flip one of the wands over so that you're dealing with the second side of one magnet and the first side of the other, they will actually try to repel each other rather than coming apart. Now, you can, if you fuss and you're patient, very slowly bring the magnets together and brute force them so that they're touching one another together, even though they're trying with the electromagnetic force to push one another apart. Now, once you've figured out which sides repel and which sides attract, you can put Velcro on them. Velcro is the key to this lesson. You put the Velcro on so that when you bring opposing sides of two magnets together, you can stick them together with the Velcro. Now, the Velcro only interacts over the shortest of distances, the distance of, well, the hooks and loops on the Velcro. And what you can do is show the students, if you can get two protons close enough together, then they'll stick together. Just like if you can get these two magnetic wands close enough together, you can stick them together. Now, I don't have magnetic wands because I have a drawer of broken magnets. And when I started teaching, magnetic wands didn't exist, and I'm still using my drawer of broken magnets. What I do have, because it's a desk toy, is these little magnetic balls that if I try and stick these things together perfectly, and I'm using gravity to assist me in this, if I bring them together, I can get them to stick together because of the Velcro in between. Now, it did, because this unfortunately is a very dry day and my glue is coming off on the Velcro, I did get the magnets rotating a bit, so the magnets did play in. So you want to make sure that your glue is really sticky on your Velcro to get this to work perfectly. But basically, you can take any two magnets and just get Velcro. It cost me 50 cents a yard at our local fabric store. You can get Velcro, cut it into small pieces, attach it to your magnets, and then you can see the force, in this case, the strong force of Velcro, is able to overcome the weaker electromagnetic force of the two magnets, allowing you to stick together two magnets where the electromagnetic force is trying to push them apart. This is a really good way to get your students to understand the electromagnetic force is trying to push apart protons, but when you get them close enough together, the strong force kicks in and the strong force holds them together, but only if you get them close enough. It's simple activities like this that can really help your kids get a tangible understanding of this is what a force is, this is how force is communicated. My Velcro is my boson in this case. It's my Velcro that's the glue on, gluing things together, and it's important that your glue is sticky. Very tangible lesson to give to your students. Now, once you've gone through and done this sort of a simple exploration to get them thinking, you can say, okay, we're going to go from using our Velcro to represent gluons to start to wonder, why is it that some atoms, our unstable atoms, fall apart? In this case, all you need is, well, I use hair elastics because they live longer. What you need is hair elastic and simple blocks. And what you'll find is as you have to stretch your hair elastic out more and more, you hit the point where you're still jamming blocks in, just like you're jamming protons into the center of a nucleus. And eventually, those protons, the blocks, don't stay inside the hair elastic very stably. The system's very stressed out, very stretched out as well. And at this point, it's unstable and will sometimes randomly, as it's sitting on the desk beside you, explode into blocks everywhere, just as nuclear reactions go on. They're less explosive, so be prepared for a lot of noise when you do this in your classroom. This gives you a chance to get your students thinking about, well, your gluon can only communicate over a very short distance. This is very tangible. And if your atom gets too big, the gluons can't glue it together. So this is a way to get your students thinking, hypothesizing over what happens when the center of your atom gets too big, doing the experiment to see what happens when the center of your atom gets too big, but not having to actually play with atoms, which is useful. From there, you can elaborate on this to start talking about the standard model, to show your students without going into detail, just like we didn't go into detail today, that there are all these other particles that we don't experience because they're not part of our stable particle physics world. We deal with electrons, protons, neutrons, they're antiparticles. We don't generally experience the unstable muon unless we're purposely building special detectors for it. You can hint at all of this. And then the final thing that I like to do with the students is to get them thinking about things like photons move at the speed of light. Photons, well, they communicate the electromagnetic force. So does that mean that it takes time for my magnets to communicate with one another as those photons have to travel between places? Yeah, that's actually something that scientists think about. And does that also mean that these bosons that weigh a lot have a lot of mass, is how we actually phrase it in science? Are these massive particles that can't move at the speed of light? Does that mean that those forces move slower when they get communicated? This is just an interesting thing to get your kids thinking about and inspire them to keep thinking about science. So, at the heart of everything we do is the idea of inquiry, getting your kids to get their hands on science. In this case, playing with magic wands, magnetic wands rather, and Velcro, getting your kids playing with elastics and blocks, and seeing what happens after they build hypotheses. The exercise that I've just outlined will be part of the Inspiring Science Education portal. It will be available for you to clone, for you to edit, for you to then upload your excellent ideas so that we can all do a better job communicating science. Now, the Inspiring Science Education website, we love it. It is so rich in information, though, that just like you probably use Google to move around Wikipedia, it's not always easy, and it isn't currently Google searchable. It isn't always easy to find exactly what you're looking for on the Inspiring Science Education website. They're working to make this easier, and while they work to make their site, which is a brand new site, easier to navigate, we're also working to make this easier for you. Everything that we do is available, also linked in to the Galileo Teachers website. And if you don't know about it, I'd really encourage you to check out this website that is a clearinghouse for teachers all around the world who are looking to communicate science via astronomy. When you land on the homepage, you can see the most recent activities. You can see a map of where the Galileo teachers are located around the world. And you can see, hey, under latest news, here's information on the Hangout that you're watching right now. If you go to resources, you'll see Inspiring Science Education is listed under resources. And when you click on that, there's a direct link to sign up for the Discover the Cosmos community, which is where we share all of our resources on the Inspiring Science Education website. And there's information on how you can earn badges related to participating in this project. There are links to our Hangouts, and there will be more links and more images as we populate this site over the months and hopefully years to come. So please take a moment, pop over to the Galileo Teacher Training Program, check out what we're offering there, follow the links to dig in to Inspiring Science Education. Thank you so much for joining us. Our next Hangout in this series will be on March 11th. We will also help you find new resources, other Hangouts that you can participate in all across the internet. So follow our blogs and check us out, as I said, on the Galileo Teacher Training page. My name is Dr. Pamela Gay, and thank you so much for joining us. And I hope to see you more online as we work to create a more educated world. Thank you so much.